CST is one of the most popular software to design and analyze electromagnetic components. And today we will learn some functions of CST. CST stands for Computer Simulation Technology. And if you are a student of electromagnetics, then this tool is definitely very helpful for you. There are a number of functionalities here, but we will only work with M microwave, RF, and optical section. And I believe that the best way to learn about CST is to do a practical work. So today we will design a metamaterial polarization converter from this paper. The paper name of the paper is Multiband and Multifunctional Polarization Converter using an Asymmetric Metasurface. And the paper was published on Nature Scientific Report. Okay, here is the design of the unit cell, and they wrote about it that there is a ground in this structure, though they didn't provide any 3D figure. Let us just imagine that there is a ground plane made of copper. The thickness of the ground plane is 0.035 millimeter. Okay, then just above it, there is a FR4 substrate with thickness H. Then we'll put the substrate above it like this. Sorry, I didn't write it in a correct way. Just understand what I'm trying to say. And just above the FR4 substrate, there will be a copper patch, these yellow lines. This orange colored part is FR4 and this yellow part is copper. And we have to draw this FSS part, and this is the main challenge of designing a metasurface. Okay, there are a number of parameters. We can see that P, that means this structure is a square, and this is A, and the radius we have to cut from this inner square is R. So if we shift R here, then the whole side will become A plus R. A plus R, this section, this inner square. So let us go to the CST Studio. Okay, microwave, then periodic structure. Then we will work with unit cell, phase reflection diagram, frequency domain. You can also choose time domain, and these are the default parameter units. You can say that time is in nanosecond. Dimensions are by default in millimeter, and I will keep it as it is. Then frequency, we can see that they have examined the result from 8 gigahertz to 20 gigahertz. So I will put it here, 8 gigahertz to 20 gigahertz. You can check this E field, H field, but for now we are just doing the basic design. So next, okay, our project template is ready. So template name is here. Okay, finish. Sometimes it takes some time. Okay, there are a number of ways using which you can design a component in CST, but mm, it's like a math. Um, we can solve a math in different ways. Similarly, you can just draw a component material according to your sense of your understanding of this software. So we'll start modeling, and we have to use mainly brick. It will create a 3D box, and this is a sphere, this is cylinder. Mainly we will use brick and cylinder sometimes. And let us define a brick, the ground first. You can see that we have to define x minimum, x maximum, and if we put numbers again and again, then this can be there can be inaccurate input sometimes. So let us define some parameters first. So parameters p, what did they say? They say that p is equal to 6 millimeter, a is equal to 1.9, p is equal to 6, a is equal to 1.9, then r is equal to 2.1, d is equal to 2, r is equal to 2.1, d is equal to 2, then h is equal to 2, h is equal to 2, then the thickness of copper is 0.035. So let us assume that the thickness of copper is T and it is 0.035. And what did we see here? We see that the one side of the inner square is A plus R, this part, A plus R. So let us define another parameter, AR, which will be A 1.9, R 2.1, so it will be 4. Okay. Now let us save the design. So we have saved the design. Now we will start drawing. So at first we will build the ground. Let us name it ground. So ground will be, the dimensions of ground is P, everywhere is, so in x minimum we'll put minus P by 2, and x maximum will be P by 2. So if we just add up P by 2 plus P by 2, the whole dimension will be P. Similarly, in y minimum, we will put minus P by 2, and y maximum P by 2. Now I will start the z-axis from 0, and I will stack up the other components above this. So the thickness of the ground plane was T, right? Yeah, T. So T. The ground plane was made of copper, so we will load copper. Will not take pure copper, but annealed. Okay, then we will load copper. Then preview. Yeah, we've got the shape. Okay. Now we will draw the substrate. above this copper ground. The substrate is also a brick, so let us name it sub for substrate, and the dimension for x min, y min, and x y are all same as ground. P by 2, uh, P by 2, yeah. Now carefully see that jet minimum will be T now, and jet maximum will be ground thickness plus substrate thickness, and the substrate was FR4. So we will load FR4 now. So FR4. We will take the loosey FR4 load. Preview, yeah, we can see that the thickness is H and it began from T. Okay. Now we have to draw the copper patch, the FSS, and the real challenge begins. You can notice that they have mentioned different values of these parameters, but they didn't mention here the thickness of the side split lines, right? We don't know this uh, parameter. Let us assume that it is 0.2 millimeter. Okay, let us just define another parameter here. W is equal to 0.2. Okay, let us save the design. Okay, then at first I will draw outer square minus p by 2, p by 2, p by 2, and minus p by 2. Now the jet minimum will be T, the thickness of ground, the thickness of substrate, and it will end at thickness of ground, thickness of substrate, and thickness of patch. Okay, and the patch is also made of copper. Let us preview. Okay, fine. At first, I will draw this two split lines. Okay, fine. So we have to cut out the inner part and we have to draw another brick. There are a number of ways you can use Boolean to cut some part out, but I will take another path. You can follow it if you want to. Cut, I want to name it cut, and minus p by 2 plus w. What is w? We have assumed that w is equal to 0.2 millimeter and this thickness. So we will cut the entire square, but we'll keep this outer line here. Okay, now minus W, Control C, Control V, Control C, Control V. Okay, and T plus H, similar as the patch. T plus H plus T. Now we will take, let's say, vacuum or other any material, because it will, if we want to overlap two material, CST shows us a dialog box where they ask if we want to cut out some part. So we have put here the vacuum. You could put any other material except copper here. Let's see how this works. Preview. Okay, fine. This is the dialog box, and this is not the correct way or ideal way to draw to cut some part out, but I really like it. Okay, cut away the highlighted shape. Okay, fine. So we got the outer part, but it is split lines, so we have to cut this part out. Here D is equal to 2 millimeter, P is equal to 6 millimeter, so this gap is of course 2 millimeter. So let us define another brick. This is also for cut, and x minimum minus 1 plus 1, 1 plus 1 is equal to 2. Then y will be, let's say, the entire part is 6. So let us just say minus 4 plus 4. This is arbitrary, you can take anything. Then again, t plus h, similar as the patch, t plus h plus t. Then again, vacuum. This vacuum will overlap with this copper, and again we will get that dialog box. Okay. Of course, cut away the highlighted shape. Okay, fine. So we got this shape. Now we have to draw this inner part and our component will be ready. Again, brick, inner square. Let us name it inner square, and the length of one side of the inner square was a plus r, right? This a plus r. So we'll take here minus ar by 2, ar by 2, and jet will be similar as the patch, as we are still drawing the patch. T plus H plus T, component copper, preview. Okay, fine. Now we got this, and we have to cut out this part and this part from here. Let us transform this inner square so that we can cut it down according to transform, translate, and let me shift it 9, preview. Okay, fine. And now I will cut this part and this part. So I will define a cylinder. Okay, outer radius is r. This r. And they have mentioned that r is equal to 2.1, which we have already declared in the parameter list. So outer radius is, of course, r. X center, this is 0, this is 9, and this is 4 millimeter. So 9, 10, 11. We want to put the center here. So for x-axis, it will be 11. For y-axis, it will be 2. And jet minimum is similar to the patch. Jet maximum is also similar to patch. And component, let us take vacuum preview. Yeah, here. Okay, fine. Intersect away. The highlighted shape. Okay. Now we will cut this part in the similar way. Cylinder, solid one, outer radius r, and x center is now, this is 9, this is 7, and y center is -2. Z minimum t plus h, z maximum t plus h plus t, component vacuum preview, yeah, okay. Cut out the highlighted part, okay. Now we will shift this back to the main structure, transform, translate, x is equal to -9, apply. -9 was an arbitrary number, of course. Okay, so our full structure is ready. You can see that here is the ground made of copper, then A44 substrate with thickness H, then the FSS similar to the paper here. Okay, fine. Now we will go save the design and go to the simulation part. Frequency, yeah, it is, we have already declared it. Boundaries, you can see that there are two pores, but as we have copper back here, we have to close it. Okay, fine. Okay. Now we will only get the results for reflection. Then home and start simulation. It will take some time, so please wait patiently. Okay, so our simulation is over and we will get the result here under 1D results and is parameters here. This is RXX, this is RYX, this is RXY, and this is RYY. All we are seeing here are reflection coefficients because we have a ground plane here. There is no transmission possible. Okay, and the results they have shown here is in linear scale from 0 to 1, and they have shown RYY and RXY. So we will see RYY and RXY. This is in dB scale. Let us see it in linear scale. So yeah, you can see that this 2 means the orange colored curve is RYY, which dropped near 16 gigahertz. This is almost similar to the given result, and the RXY is also near 1 in this position. There is a small mismatch in this result and the result the paper presented, maybe because of our assumption here. We have assumed the thickness of this outer split lines is W, but maybe this is of different thickness. So anyway, we got the result very similar to the published one, and we can say that we have successfully designed or recreated a polarization converter, metamaterial matters. Yeah, designed the Metasurface. So congratulations.